Welcome everyone to this recorded session of the 565 CUDA Debugging Lab. We'll start with a few slides to give you an overall view of what CUDA debugging looks like, and then we'll dive deep into showing what the Visual Studio Insight can actually do. So on today's list is talking a little bit about debugging tools on a very high level overview. Talk about the Visual Studio Debugger a little bit to show you how the CPU side of debugging works, and the Insight Debugger to show you what the CUDA side of debugging looks like and how to manage millions of threads running at the same time. So with these tools, you can figure out things like incorrect launch configuration, your thread indices, block indices. You can figure out synchronization problems or atomics, and find where your problem lies and correct that. So in practice, most of us probably follow this order of debugging. As soon as something's not working, you probably add a cout or a printf and figure out what the values are where. And this works, but it doesn't scale. For that, having a proper debugger like the Visual Studio Debugger is much better because you get to walk through it. In practice, I always recommend that if you're writing any kind of algorithm, it is always good to walk through the debugger to ensure that your algorithm is working as expected. Even if the output is you think is correct, make sure that you're walking through the debugger and evaluating each step. Uh, However, when it comes to GPU programming, Visual Studio Debugger doesn't cut it. Although it can do multi-threaded programming on the CPU side, it can't really debug the CUDA side of things because it needs access to those resources. That's where Nsight comes in, which allows you to debug the CUDA side of programming along with profiling and other graphics tools. So other debugging tools that exist on the host side are the Visual Studio Debugger, as we spoke about, GDB on Linux. On the device side, we have the Nsight Visual Studio Edition, Nsight Eclipse Edition, and CUDA GDB, which is essentially GDB but for CUDA programming. So this is something we'll discuss in class about which debugging tools do we know and commonly use. Printf, cout, stream, these are all programmable tools. So essentially, you're putting these in your code to get some sort of an output. Breakpoints, conditional breakpoints allow you to step through your code. Call stack shows you the function stack that you're using currently. And Auto's local watches are windows, Visual Studio based windows that you can see what the variables are. So on the CUDA side, you can debug using Nsight or CUDA GDB. To profile, we have the NV Visual Profiler, or NVVP for short. With Nsight, modern tools now include Nsight Compute and Nsight Systems to help you do deeper profiling. And the CUDA SDK also provides an Excel spreadsheet called the CUDA Occupancy Calculator, where you can plug in things like how much memory you're using, how many registers you're using, to figure out what the optimized occupancy calculator is to get the launch configuration that would work best for your kernels. So just going through a high-level overview of CUDA GDB, which is on Linux, because we won't dive deep into it in this recorded session. CUDA GDB is an extension of standard GDB on Linux, which is a command line debugging tool. It allows you to debug code on actual GPUs, so you're getting the values read off the GPU itself. And it can debug both the CPU and GPU code, so you don't have to switch between GDB and CUDA GDB when you're trying to debug. Setting the compile flags is easy. You add the small g and the capital G flags to generate sim debug info for both the CPU and GPU side. And all the usage for CUDA GDB is very similar to GDB itself, in the sense of breakpoints, shortcuts, walking through lines, and jumping around. So if you're used to GDB, CUDA GDB could be a great tool. I would always recommend using Nsight for CUDA debugging, even on Linux. But if you want to try out CUDA GDB, then there are plenty of resources online or you could send me an email. A few terms that you should know before we dive into Insight are software coordinates and hardware coordinates. Thread blocks and kernels, you know of already, we've gone through this in class. Um, on the hardware coordinates, when you're debugging code, you're going to see these be used a lot more, where a lane is a lane where a thread is executed. So you're always going to have a one-to-one match between lane and thread. Warp is a set of 32 threads that execute together, and many warps make up a block. SM is one streaming multiprocessor on a GPU. Depending on what your GPUs, you may have anywhere from 2 to 16 or more SMs on a device. And of course, device is the GPU itself. On a high level, Insight can do help with both debugging and profiling tools. It has a GPU debugger, a graphics inspector, and system profiler. And new tools also include Insight Systems and Insight Compute. So feel free to try these out. I've linked to the user guides for both the Visual Studio and the Eclipse edition for you to try. So how do you set debug info um, before you can actually use the Insight debuggers? For all the class projects, we do this in CMake by adding the flags. Otherwise, if you're using your own projects, then these are some of the steps that you need to follow to enable the debug info. And follow these steps as well, where you're generating the debug info for both the host and GPU side. And make sure to set the correct compute capability, because if you don't do this, you're not going to get the correct hardware codes back and you'll see bad information. So with that, let's dive into Insight itself and walk through what information it can give us. So let's look at Insight and what it can show us. First, I have Insight installed in my Visual Studio 2017 edition. So I'm going to go in and go into Windows first and see System Info. So let's walk through that first. When you open this, it's going to show you all the hardware information. So we start with the System tab on the left. This is going to show you what hardware information is there for your laptop or desktop. So you can see the number of cores on your CPU, the total physical memory installed. So I have 32 GB. It shows you hybrid graphics if that's available, your Windows version, and the Insight versions. The display devices tab shows you all the GPUs that are available. So in this case, it's showing me the Intel UHD graphics that I have built into my Intel CPU. Um, and then if you go into NVIDIA GPU devices, this is going to show you information about your specific GPU. So I have a GeForce GTX 1650 installed. Um, the driver I have installed is 452, which I believe is the latest. Driver model, there are two driver models that NVIDIA follows. WDDM, which stands for Windows Display Driver Model. And if you're using an NVIDIA GPU for display, that's the model it's going to have. And the other one is TCC, which stands for Tesla Compute Cluster. So if you have GPUs that don't have displays or are using a remote GPU, sometimes these GPUs can go into the TCC mode, which means they don't run graphics applications but can do compute-based CUDA applications. The CUDA device index starts from 0 and increments for each individual CUDA GPU you have. I have only one GPU, so that's going to remain 0. The GPU family gives you information about the GPU's architecture. So my 1650 GPU is a Turing class architecture. So and the architecture specific architecture in Turing is 117-A. So if you have a Pascal GPU, it's going to start with a P. A Kepler GPU is going to start with a K. Maxwell GPUs will have Maxwell architecture codes. This compute capability is important to note. It defines the architecture once again, but in a way that the system can read. You can find this on the web as well, what your compute capability is. So Kepler was 3.x, Maxwell was 5.x, and then Pascal was 6.x, and Turing is 7.x, and the new Ampere GPUs RTX 3080, 3090 are going to be 8.x. So number of SMs is the streaming multiprocessor. So these are individual units of many CUDA cores that form a multiprocessor. So knowing this number is also important. So I have 16 on mine. I have 4 GB of GPU RAM. This is my frame buffer bandwidth, which is essentially the the maximum copy speed if you were to copy memory from the device to the device without actually going to PCIe. So if you were just copying two arrays or one array to the GPU again, this is the maximum speed of copy that you're going to see. And we'll revisit this in the performance lab. Um, these three numbers are your speeds, clock speeds that you can get. These essentially go into how many teraflops you can expect. So when you're doing something like matrix multiply, you would use these to calculate what the theoretical maximum of your GPU is. And the runtime, of course, is GDDR5. You may see GDDR3, GDDR5X, GDDR6X for new GPUs. So feel free to. Um, it doesn't really matter in code. It just defines how fast your memory can be. So moving on, this is a key tab for you to know. This shows you the CUDA information for your GPU. So we're going to go through a few of these, not all of these. Um, and so let's start with the top, and we'll go in alphabetical order. So async engine count, it defines how many asynchronous operations you have. Most of the start of the semester, we're going to do synchronous operations, but once you get to advanced CUDA, where you can do compute and copy at the same time, this defines how many of those operations can be happening simultaneously. The clock rate is the same as the GPU device clock rate, so 1560 megahertz maps to this number here. Um, compute capability major and minor are there so that you can use this programmatically. This again maps back to the compute capability number here. Compute mode is 0 for WDDM models and 1 for TCC models. Concurrent kernels again goes back into the async engine about how many simultaneous kernels you have running. So in this case, my GPU has one. This is the GPU name. So if you were to query the CUDA properties for the GPU name, you would get this back. The global memory bus bandwidth, again, if you want to use it programmatically for advanced programming and to figure out how much time you would need to copy something, then this is something you would use. These Now, these numbers are important to note as well. These define the maximum block and grid size in any one dimension. Note that these don't define the total number of blocks or threads you can have, but defines what the maximum is per block. So if we look at the block numbers, you can have 1024 in X, 1024 in Y, and 64 in Z. That doesn't mean you can have 64 million threads in a block. What it means is you can have a configuration that is 1024.1.1 or 1 or if you have 1.1.64, then you only have 64 threads in a block. These are the maximum per dimension. The maximum per block remains 1024. And similarly with this, the number of blocks in a grid are defined, the maximum number of blocks in a grid are defined in the dimension. It's a large enough number that you never have to worry about it. Coming to some of the memory resources, here these essentially define how many registers and shared memory you can have per block and per multiprocessor. So multiprocessor is the hardware SM, and we'll talk about this more once we get into the advanced programming about how CUDA kernels map onto multiprocessors. But for now, keep an eye on this block, which essentially defines how many registers you can use in a kernel per block. And in this case, for me, it's 64 kilobytes. And if you exceed this, then CUDA is going to have to reduce the number of uh, active blocks that are executing in order to manage the resources. We haven't spoken about shared memory yet, but once we get to it, have this number in mind, and we'll talk more about it then. Um, the the other thing that we spoke about before was the number of threads per block. So in my case, it's 1024, and for most, if not all the GPUs, it's 1024. The number of threads per multiprocessor, which is again the hardware concept, is also 1024 for me. So once we get into advanced CUDA, where we are determining how many resources we have, this number would play there as well. Again, multiprocessor count, another programmatic way to access this. Um, this number is useful to know too, especially if you're doing double precision programming. What this tells you is the speed slowdown for doing single floating point versus double floating point precision computation. So 32 means a double precision computation is 32 times slower than a single precision computation. And compute stands for a multiplication or addition. So if you by mistake use doubles instead of floats, you're going to see the slowdown happen very rapidly. Finally, warp size. This is going to be 32. It's been 32 for the longest time, and I don't believe NVIDIA has any intention of changing it. Now you can find OpenCL information here too. It's generally going to map straight to the CUDA information you have. It's just different definitions and how you access this programmatically. And you're also going to see the Intel graphics card show up here because OpenCL is platform agnostic. So one thing I want to show you before diving back into Insight is the CUDA samples. And these are generally available at C Program Data, NVIDIA Corporation's CUDA samples, and the version number of your CUDA SDK. Now, obviously, if you have these on a remote machine where you don't have access to the admin panel, it would be best if you go a step up, copy these, and paste it into your local directory. I don't have to do that because I'm using this on my own laptop. So what I'm going to do here is open utilities and open up device query and open my Visual Studio version of the solution. So in the CUDA device query project, what it shows you is how to query device information programmatically. So we saw how Nsight shows the information as a table, but you can query this information directly through the APIs as well. So you can make runtime decisions based on what GPU this is running on. So you don't always have to know which GPU it's on beforehand. You can do this programmatically. The important um, structure here is called CUDA device prop, and you can find complete information about this structure on the CUDA SDK documentation. And the way to populate this CUDA device prop is to use this CUDA get device prop function, pass this as input, and pass the device ID. So this program is iterating over all the CUDA devices available. On my laptop, it's just going to be one. But if you have a multi-GPU system, then it's going to iterate over all of those. It's and once this device prop is populated, it's going to have a bunch of properties that we can look at. Name, of course, and you can get the runtime versions. You can get the number of GB of RAM, the number of cores and multiprocessors. You can get clock rates, cache, and other information that's all here. So let's go ahead and run it. And as you can see, this is all CPU side code. There's no GPU code running here. So looking at the output, you can see that this is of course formatted using the printfs, but this gets you pretty much all the information that you had through the table, but now it's done programmatically. So if you, let's say, wanted to understand the amount of global memory available before you ran a system, ran your kernels, you can do this programmatically and then adjust how many kernels or threads you're launching. Similarly, for the number of multiprocessors, for me it's 64 and 64 CUDA cores per multiprocessor, but this can be different on different GPUs. So this is a great thing to do when you're optimizing your CUDA kernels and CUDA programs. So here I've opened up the CUDA documentation. So this is both the API documentation and performance and optimization guides. It has the runtime API, driver API, math API, which are the math functions, and gives you the API for all the libraries. So some of you may have used cuBLAS or cuFFT, um, and others. So this gives you all the API for that. It gives you samples, demos, and how to optimize your program for each architecture. So if you're targeting a specific architecture for your program, it gives you the guides on what settings you should use and how you should tune them. Also has the guides for compilers, Nsight, Nsight Compute, and others. So this you can't spend enough time on this. There's so much to learn here. So please use this as much as possible. For this specific debugging um, recording, I've opened up the CUDA device prop that we were just talking about. So exploring this page will give you all the information about each of those properties that are in the struct, so you can use them programmatically. And finally, coming to the Insight Visual Studio Edition, this is the documentation for that. Everything from installation to compiling, running, debugging, profiling, inspecting the states, inspecting memory, all of that you can find on this page. I'm also using this page as a guide to doing this recording itself. So I have project one CUDA Boids open here. We're going to be using this for showing how Insight and Visual Studio Debugger works. Make sure you're on the debug configuration here so that all the debug symbols are compiled into the code. If you're in one of the release ones, then the symbols are not going to be loaded and either you won't hit the breakpoints or you'll see garbage information. As you can see, I've set a breakpoint here, which is on the host side. The great thing about the next-gen debugger is that it can do both host and device-side debugging, so we can get started with that. I've pre-compiled the code to save time, and I'm going to get started with the CUDA debugging side of things. So we've hit the breakpoint here, as you can see. And before we start walking through the code, I want to show you a few windows. So if we go into debug windows, um, some of the best windows here are watch, and you can have multiple watch windows, autos, locals, and call stack. So before we walk through, let's walk through these windows itself. So call stack shows you the depth of the function calls you're making. So right now we had main which called init. So we are seeing that here in the call stack. So as you call more and more functions, this will get populated. The autos window shows all the variables that are currently in scope. This is uh, there's a select set of variables that are picked by Visual Studio based on the line you're currently at, and giving you the variables that are probably most pertinent to debugging. You can't add more variables here, but it's a quick way to get started with what Visual Studio pretty well picks the relevant variables. And then if we go into locals, these are all the variables that are in scope within the function. So for example, if you had, let's say, a for loop or an if statement and you were defining variables within those blocks, then those variables will be shown in locals when you're in those blocks, but rather, and will get removed when you step out of those. You can see all of them. Again, no, you can't add any more here because Visual Studio is picking all of those for you. And these are going to be the top level. So if you have any arrays, you'll have to expand these to know more about them. The watch windows are where you can add more variables. So I'll get to this in a second. So let's walk through this, and I'm going to step through, and I'm going to go to the locals window just to keep an eye. And as you see here, if something changes to red, that means the previous line has just changed that value. So we set GPU device to 0. And in the current line, we're going to set device count to 0. So I'm going to highlight this line here, and you can see it's some garbage value. And now as I step through it, it's changed to 0. And you can see that it's red because it's just updated. Let's keep stepping through. And now that we are at CUDA device prop, and CUDA, the device prop variable is going to get populated, I'm going to highlight that and expand it just to make sure that we are seeing the right information. And as I step through it, you're going to see that the entire struct has been updated. There might be some variables here that won't get updated. For example, max thread dims is probably the same by default and same for the GPU. So that's going to remain same, and thus you're not seeing that change to red. So I'm going to keep going on, and I'm going to come here because there's a nice trick I want to show you. So if we go into into the watch window, and let's step through one more line. So now we can see that device name has been populated. So I can type device name here. And this shows you the entire string. And you can see that the type here is highlighted as an STD string. What you can also do is do something like 0 there. So now you're only getting the first character. So now you can see that the type is char. Um, and although I'm showing this with a string, which is essentially a character array with other functions around it, this works with other types of arrays too. So if you had like a vector or floats or a regular integer array, these tricks would work there as well. So what I can do is I can say device name, comma, 10. So what this is doing is asking for the start of the device name and 10 elements after it. So when I hit enter, you can see that this goes to 565 space CUDA, which is another 4 space I. So that's 10 characters. So you can do this with float and integer arrays too. So the other thing you can do is if I were to get the C string behind this, which is the regular char string, and do the comma 10, it will still work. So now you can see that this is const char 10 as the type. And then if I do, let's say, plus 5, this is adding an offset to the start of the string. So instead of seeing 565 CUDA I, you're going to see the first 5 characters disappear. So until C will be offsetted. So we'll see that the new watch variable starts from U. So I'm going to hit enter now. And now you see that it's UDA space intro with a colon, which is again 10 characters. So this works with other types as well. So although I'm showing you just char, it will work with other array types as well. All right. So with that watch shown, I'm going to go into the kernel side of things, and I've placed a breakpoint here. And the reason it gives me this error is because the execution is currently on the host side. So you can see that up here in the thread, it says main thread, and that's why this is showing that this breakpoint won't be hit. But we know that it's in a kernel and it's going to run. So I'm just going to hit continue, and we'll see that this breakpoint would be it. There you go. All right, so let's jump back into our autos. So the great thing about Nsight is that it uses all of these same windows as Visual Studio does. So we are seeing that all of these autos, locals, and watch are still populated. Of course, watch is going to be useless now because that was populated with the old variable. So I'm going to delete that. But now if we come back to autos, you're going to see the block IDX, block dim, and thread IDX for the active thread. Now remember that when you're in a kernel, there is a warp running. So a warp is 32 threads, but each of these breakpoints is at a specific thread. So we are seeing that the current active thread is 000 of block 000. So that's important to remember. Make sure that when you're debugging, you're on the right thread that you want to be. So let's see, just like the debug had windows, Msite has a few windows too. So let's jump into that. We've already seen system info. I'm going to open warp info now. So like I said before, a warp is a set of 32 threads that execute together on the GPU. This tab is going to show you all the warps that will be launched for the current kernel. And you can add a filter here that you can type out. We're not going to get into that right this moment. The important things here are the shader info, which shows you the block and the thread ID, block IDX for the entire warp. A warp cannot be split across multiple blocks. Each warp is within the same block. And the thread IDX of the first thread in that warp. Um, so you're not going to see the offsets you're going to see between each warp are 32 because the warp size is 32, and you'll see that these are 4 groups of 8 just for visual representation, but in total 32 threads. So CTA is the block index, and thread it shows you the thread index of the first thread in that warp. So the other thing you can do here is, if you wanted, you could double click each of these boxes, and you can go to that thread if you want. We can do that later. The other windows here are warp watch, which is the same as the regular watch, except that you can add CUDA variables on it, and you'll see that each of these has 32 rows in it. So you're going to show the entire warp. So if I pop this out and populate this, and let's go back to the kernel. So I can add a variable like index and maybe step down so that it gets assigned. So now that you can see that we are in a standard index equation. So each of these values is unique and populated now. So that's warp watch. Let's see what are the windows are there. Let's go into lanes, and let me bring that there. So like I said before, lanes is a representation of the threads in hardware. So you're going to see each one of them has thread index. And this is going to show you what state they are in. So in CUDA, you can have branching warps. So this is a great way to know which threads are active, which thread has the breakpoint, which threads are inactive. Um, so that's lanes. Let's go into resources. And this has a few tabs in it, so I'm going to put that there. And I'm going to put this here too. So in resources, we have a few drop downs here, and I'll walk through some of them. Devices is going to show you the same information about the device it's executing on. So just like we saw inside Windows System Info, that you're going to get to see here as well. Context, you can have multiple CUDA contexts for multiple threads. So that's going to show you, in most cases, you're just going to have one context. Again, streams, you can have multiple streams going on for increased efficiency and optimization. We'll get into this later in the class. Functions show you all the device functions. These include both CUDA and, global kernels and functions. So you can see the name here, the demangled name, which is the full definition of it. Mangled is the name in the object code. And you can see the number of threads per block, amount of registers they're using, the number of bytes. So we're not using too many of these, but as we advance our understanding of CUDA, you'll start seeing these be populated too. I'm just going to find the one that we were currently using, which is current generate random position array. So let's go into resources. I'm going to sort by name for that so that it's easier to find. And yeah, current generate random position. So here we can see that once I go back, you have an index defined. You have one, two, three, three variables coming in as function arguments. So that's 24 bytes, and then you have a vector pointer as well, which is going to be additional bytes. And then we have another 4 bytes for the index and another vec3 being defined in local. So if we go back to resources, this is telling us that each thread is going to use 29 registers and 184 bytes of local memory. So that's a great way to find out what your resource requirements are for each kernel as you write them. So I'm going to skip graphs right now because that's when you use graph functionality for like machine learning. So that's not necessarily important for debugging right now. So let's see what other windows we have. And finally, we have GPU registers, of course, which give you all the register information. This may be hard to read right now because it's all in hexadecimal and registers. But once you get used to advanced CUDA programming, you'll be able to decipher this pretty easily. All right, so I'm going to close most of these. So I'm going to close GPU registers, lanes, resources. I'm going to keep warp info around and warp watch around, and I'm going to split the window so that we can see both sides. So I've already added index to the warp watch. Just for showing you, I'm going to also add time and scale because these are input static variables. So these are going to be same for all the threads. So I'm adding time there, n and scale. And you can see that these are all going to be the same. So I'm going to, again, back delete these because they're not necessarily important. I'm going to add in block IDX and thread IDX. Now, although these are 3 component structs, the watch window is going to be showing them pretty easily. So you don't have to do block IDX.x, although you can do them if you want. So I can show you thread IDX.x, and that's going to be unique. You don't have to. You can do them as 3 component structs. So let's step down. And now we can see that we are about to generate a random number using this function. So if we peek definition here, we see that this is a host device function, means it's going to run, it can run both on the host side or the device side. And it's going to generate a random 3 random components and return a vec3 for that. So I'm going to close that. And I'm going to add rand here. Now, remember that this is a GLM vec3, which is coming from the GLM library, so this may not show up directly. So as we see, this is a local T vec3 here, but the debugger is not able to see the right values. So how do we get to see this? What we can do is open a double bracket, do underscore underscore local, and we are doing local because rand is local to the kernel here. It's not coming in as global memory, or it's not shared memory, it's local. So I'm going to do that. I'm going to do float star to typecast it, and I'm going to put an ampersand to get the pointer to it. And I'm going to close that bracket as well. So once I hit enter, now you're seeing that this is a memory address now. Now, if I add 0 of index, this should convert to values. There we go. So now all the values are populated for all the threads here. I'm curious why these are zeros, but I assume the GPU hasn't sent that information back. So we can do the same for, oh, you know what? These are zeros because not all um, registers may, or not all threads are using the same pointer probably. That's why. So it's using the address for rand from thread 0, but not populating it correctly for the other threads. The other way to do this is if you want to copy this and put it into our watch window, that works as well. So here we can, I'm going to copy that again. So, oh, this is what I made a mistake. I did of index where I should have actually done 0 because the rand is XYZ. So we can also use 0, 1, 2 and that's why it's probably running into garbage. So now if I do 0, then all of these values are populated correctly. So we can do the same thing for 1 and 2. So let's squeeze that back in. Um, so that's how you would read GLM vec3s. So now let's step down so that values are getting assigned to ARR, which is the global array. So if I type ARR of index, the thing is ARR of index is also a GLM vec3, so we are going to run into that same issue. Um, However, we can't use this local uh, descriptor with ARR because it's not a local variable. It's a global variable that's coming in through the function pointer. So to visualize this ARR global memory, what you're going to do is go into debug, Windows, and you're going to see this memory, and you can open one of these watch memory windows. And then what you have to do is in this address field, get the address for ARR. So if we highlight it, you can see it, or you can copy it from this box here. So I'm only copied the hexadecimal part, and let's put it there. So normally this is set to 1 byte integers. I was testing it, so I switched to 32-bit floating point. We know that GLM vec3s are 32-bit floating point, so we're going to set it to that. And because we initialized this on the host side to be all zeros, this global memory is all zeros. So now if we step into the next line, you're going to see the values update. Now you can see this that some values update, but it doesn't seem to be in any regularly pattern. Can any of you think why? I'll give you 3 seconds to pause this video. 3, 2, 1. So remember that we are not, you know, we only assign the X components, and these GLM vec3s are 3-component structs, right? So you're going to get XYZ, XYZ, XYZ. So if you see, the first value got updated, but 2 zeros, then one value, then 2 zeros, so 1, 2. So what we can do is, because we know this is a vec3, we can change the number of columns to 3. So this fills to 32, so I'm going to backspace as and hit 3. Now you can see that all the first column values have been updated, and only 32 of them, because we are running a warp, so 32 threads have executed and updated the values. Let's do another line. So now you can see that all the Y values are updated. And let's do, if we do another line, then it may exit the kernel because we are done, and the execution on the kernel will end. So we may step out of this. So pretty a warning before we do that. So I'm going to do next step. Okay, so we've updated and it hasn't exited. So that's great. So you can see that the red values have changed. So that's one way to visualize global memory using this kind of memory watch. So and I'm going to pin that here so that we don't lose it. So once we have that, I'm going to stop this. And the other way to visualize global data is to use a float3. So float3, or I'm going to type this again. So if I type 1, you can see that there are multiple float1, float2, float3, float4. These are intrinsic variables in CUDA. So the debugger and CUDA understand them. So we can do float3, temp value equals. Another built-in function in CUDA is make float3, because and then we give it ARR of index dot x plus, or not plus, ARR index dot y, ARR index dot z. So if you do this, float 3 values will inherently be visible in the what watch and in auto, so you can use those as well. So that's another way to visualize data without having to go into the memory window, which could be confusing or may have way too much data to look at. So the other thing I want to show you is about branching. So since we've made changes, I'm gonna first go ahead and compile this. Um, so our size for generating these random numbers is 5,000, so n is 5,000. But if we look at our block size and block threads, we are launching 40 blocks of 128 threads each, which results in 5120 threads in total. So that means we are launching more threads than we have elements. So some threads are going to meet this condition and exit. So that's called branching or early exiting. So I'm going to put a condition here and add the expression index equals 4999 because 5000 would be exceeding this condition and 4999 would be within it. So save that and let's start debugging this. So as we look into the kernel and we hit the breakpoint, and you can see that this yellow arrow is marking where index is 499. And look at this, all of these are grayed out. Even though the index is populated correctly, all of these threads are grayed out. So let's look at lanes. And this is interesting too. So all of these threads are marked as inactive. And if you look at warp info, um, the other thing to note here is that all the other warps that were before this have completed their tasks and exited. So we see a few green here which are active, and the grays here are essentially inactive. So what do we mean by inactive? If we go back to our kernel, um, any threads that don't meet this condition have nothing else to do. So they are exiting. And that is called early exiting. So it's a way to optimize your kernels. Now, if there was an else condition here, if index less than n, else, do something else, that would be called branching. So in that case, some threads in the warp are doing one thing and the other threads are doing another thing. That's called warp divergence, and we'll talk more about this in class. So if we step through this, we can see that some values update and none of the other threads are doing anything else. So I've closed the project one, and now I want to open a simple example from the CUDA samples, which is vector add, to show you some of the more basic things without going into GLM, vec3 and stuff. So I'm opening the 2017 version of vector add. Let's open the file, compile it. And while that happens, I'm going to place a breakpoint here. So in this kernel, we have 3 global memory arrays coming in and all are float. So let's see how we can visualize simple arrays like that instead of having to go into GLM vec3s. All right, so let's start debugging this. All right, let's step down one and let's add block idx.x and thread idx. If you double click these tabs, they'll auto size. So I use that quite often. And then we want I, and let's go for A of I and B of I and C of I. Now, I assume your first question is, hey, why is A, B, and C working here when it's coming from global memory, but when we were trying to access ARR in the Boyd's example, it didn't work. That's because ARR was a GLM vec3 and there are the watch window didn't exactly support that struct. So that's why we couldn't visualize it. But here, that's fairly simple to do just because these are types identified by the watch window. So we can step through this quite easily. And as we step down, then we see the values getting updated. So now that C is updated, let's see what happens when we go beyond the execution. So in a normal function, this would just return to the next, it would step out and go to the next statement of the previous function, but this is a CUDA kernel, so there's more threads to execute. So let's go into locals or add a watch for thread idx dot thread idx and block idx. I'm not using this because this is also going to change. So keep an eye on this. So thread IDX is all zero, block IDX is all zero. So let's step down. So let's see what happens. So now what's this? So thread IDX has increased to 32, which means we are in warp one. So let's go back here. And you can see that I can't scroll up anymore. And there's no 0, 0, 0, 0, 0, 0 for the first block, first warp. That has exited. So now we are looking at this warp. Now, how can we, instead of going to the next warp, is there a way to go to the next block, for example? So to do that, go into Insight, and you can either jump the warps here if you want, if they are active. So the previous warp is no longer active, so this doesn't really make any sense. So, but if we want to, let's say, jump the block, what we can do is come into freeze and do scheduler locking resume block. Okay, so keep an eye on this now. 3200, right? So let's step through this. And none of these change because we are still on the current same thread. So now what happens? Let's step through that and look at this. Now block IDX has increased to 1, 0, 0, and thread IDX is 0, 0. So that means instead of jumping to the next warp in block 0, we jump to the next block. So if we go back into our warp, now look at this. I can't scroll up anymore, but all the 0, 0, 0 blocks are gone. And now we are at block 1. So let's try that again. So step down, step down. Now what do you think will happen here? Take a guess. So this is increased to 2 now. Again, staying at the first warp because we are essentially starting a new block. So only the block index has increased. So let's change the freeze mode to resume warp. Let's see what happens. So I'm going to step down now, and we are on the second block, 0th warp. Let's increase that, and now we go to 32. So we've changed the warp. We went to the next active warp. So if we go here and look, the starting index of that is 32. So similarly, we can have different locking and different warps. So feel free to try this out at your own convenience and see what happens when you choose different freeze options, as these are called. The last thing I want to show you for today is how to add um, command line options when you're using the Insight debugger. So you go to this button here, Insight User Properties, and you can use this working directory and working environment and add command line arguments here, which are generally picked up from the Visual Studio debugger. So if we go to project, escape that, properties, and go into debugging. So if you add any arguments here, that's going to get picked up. But if you want to add specific Insight debugging arguments, then you can add those here as well. So that's another useful tool for you. So that's all for the debugging session for now. If there's more questions or more things and tips and tricks I can share with you, I'll do that in class. And as we do more advanced CUDA learning, getting into warps and scheduling, you'll understand how to use these tools more to optimize your CUDA kernels as well. So please bring any questions you have to class. I'll be sure to cover those, but I may not repeat everything that we've done in this recording in the class as well.